plenary talk is by Professor Alberto Grünbaum from UC Berkeley, and he will speak about time and band limiting, finding differential operators that commute with naturally appearing integral operators.
Okay, well, thank you very, very much. Thank you for everyone that is listening. Talking about time limiting, I will do my best to try to finish, if I can, 10 minutes early, so you can have a better lunch that way, okay? I'm not promising on limiting the band, but at least I can limit the time. So thank you to the organizers for inviting me. You may regret having done this, but anyway, it's too late to make a change now. So let me start, and I'm going to make lots of technical mistakes, so just bear with me. So I will not go into any of the technical parts during this talk. If anybody cares, there is already an online paper in the journal Inverse Problems, and you may want to look at that if you want, okay? Now, I want to dedicate this talk to a couple of friends of many of you too, I'm sure, who have passed away within the last year, more or less. And these are Harold Whittam and Henry Landau. They used to come to these IOTA meetings from time to time, certainly more than I did. And you will see that their work has been very inspirational for me, and maybe for some of you too. So when you pick a title for a conference like this, then you regret later on you should have picked a different one. So this is an alternative title for the talk, and it could be Miracles in Signal Processing and the Role of the Korteweg-Lebris Equation, okay? So if I can explain at least the title of the talk in the next, 50 minutes, I'll be very pleased. So in the case of signal processing, the initial work appears in several papers at Bell Labs around 1960s, and they are works by Slepian, Landau, and Pollak in different combinations. I learned of this material from a very, very nice book that I'm sure some of you may know, by Harry Dim and Henry McKean. Henry was my thesis advisor a long time ago. So was Harry, by the way. Harry was also a student of Henry. And that book is full of little gems. And this is just one of them. Now, way back, somebody mentioned that this meeting started in 81. Well, around in the mid-70s, there was a development that had great impact in terms of how mathematics is used in the real world. And it has to do with the appearance of so-called X-ray tomography. I got involved in that area very early on and wrote a couple of papers. I wrote a few more, but the ones that motivate what I'm going to be talking about are basically, is really the first one. Then there was a paper with Mark Davison, who was a student of mine in Berkeley at the time. I'd probably take 10 seconds to mention my debt to him. I didn't have any money to hire a student then, but he was a very enterprising guy, and he was hired by a bunch of geophysicists at Berkeley. They wanted to find out, using this new tool, X-ray tomography, how does a crack develops inside a rock. So they had a huge rock. They would start pressing from the sides, and presumably a crack would form inside. And if you keep pressing, eventually the rock will break, and you can see everything has gone to pieces. Fortunately, they didn't have access to a medical device. They had access to a very old X-ray machine that could swing around the rock about 45 degrees. So that led us to talk about limited angle image reconstruction. And the reason was not that in the hospital you were looking at the patient only from certain angles, but that in the case of this geophysics situation, you could only look from if I remember right, it was 45 degrees. And that led me to all sort of other things, including the stuff that I'm going to be talking about today. So let's look at a modern CT scanner. If you go to a hospital, as some of us with age do a little bit more often than we wanted to, this is the way a CAT scan looks like. Now, if you were to open this gantry here, something you're not allowed to do, you will see this. So I've taken off the cover, and inside, this picture is pretty bad. You have an X-ray tube that is emitting X-rays and is moving, in theory, all the way around the patient. Okay, it goes like that. And in our case, if you want to think of this in this way, we could not really go all the way around the patient. That has to do with one of the words in the title. The title talks about time and band limiting. Maybe the time takes here the role of the angle, okay? So the question that I really wanted to answer is the following. It is clear that if you measure more, you should get a better picture. So what's the relation between the radiation you're subjecting the patient to and the image quality? Is it true that if I increase the angle, mathematically you can prove that it doesn't matter, even if you have a very small angle that you're going around, you can still do the inversion. But this is only true mathematically. In practice, it's a very different story. So is it true that by doubling the amount of data that you collect, the image will get twice as good or not? Anyway, so what I am doing now is going back in time. I mean, that question that I just formulated was not original with us, of course. Hardly anything is original these days, or ever. It was already asked by people like Shannon and others. So let me put this, let me give sort of the entire talk in a few slides. So you have any signal processing problem, and you measure some data. E is an operator here that describes the setup that you have. And let's assume that it is a linear operator. F is the unknown function you're trying to find. And usually, most of the time, the data is incomplete and noisy. So how do you deal with this problem? Well, you can go back to Gauss or maybe Euclid if you want to think about this. You should consider the operator E star E in some appropriate mathematical formulation. Now, what happens, and we will see this very, very clearly, this E star E is a global operator, normally given by an integral kernel or a huge full matrix, say 1,000,000 by 1,000,000. And you need to compute the eigenfunctions of this integral operator or large matrix efficiently and economically. And these are, of course, the singular value, the singular functions of our problem. Now, here is a problem. This operator turns out to be self-adjoint, but it really has only a finite number of eigenvalues that are truly non-zero. That's what I mean by significantly non-zero. There's a spectral gap here. After a few non-zero eigenvalues, all the other ones are of the order of 10 to the minus 12, something like that. So computing the eigenfunctions will be a real problem. Spectrum accumulates at 0. And now you can think for a moment and discover that any reconstruction algorithm that you want, which is stable, should not try to find the object itself, should only try to find the projection of that object on the linear span of those singular functions that go with the truly non-zero eigenvalues. Mathematically, they're all non-zero, but 10 to the minus 12 is really 0. And now, why do you do this? Well, the quality of the images will depend on what is the linear span of these good eigenfunctions. If you discover that that linear span is fairly small, then you have to measure more. You have to start from scratch, compute the eigenfunctions all over again, and discover what happens in that case. But here, so you will have to do this maybe a few times and lots of them. Now, because of numerical reasons, finding the eigenfunctions of these integral operators is an extremely ill-posed problem. The reason is that the spectrum concentrates at one point. The fact that it concentrates at 0 is not relevant, but they happen to concentrate at 0. So here comes a miracle. I mentioned the word miracles in signal processing, and here is the word. The miracle is that you can write down, and we will, a differential operator of order 2, actually, which has the same eigenfunctions as this global operator here. But more is true. Actually, these two operators will commute, but they have simple spectrum, which is very important, and even more important, or equally important, is that the spectrum of the differential operator is very, very spread out, whereas the spectrum of the other guy accumulates at 0. So I claim you cannot ask for more luck than this. So I read of all these situations in this book by Dean and McKean years ago, and I was always tantalized by the question, what is behind this miracle? The miracle was discovered by lots of people, Slepian, Landau, and Pollak. I'll be very specific in a moment, okay? And I found this relevant in the case of X-ray tomography. And I'm sure this is relevant in other situations too. So what is behind the miracle? I have to say, after more than 40 years of looking at this, that nobody knows. Okay, so I don't have, if somebody can give me a good reason why this should be true, I can stop the talk right now. The fact is, I don't really know. Okay, so that's essentially the talk in a few slides. So I've been looking for other situations where this very exceptional miracle holds besides the case that had been found by Slepian, Landau, and Pollak, which I will talk about in detail in a moment. And what I can say after 40 years is that one miracle begets another miracle. It is something called the Korteweg-de Vries equation. I'm going to make the assumption that you guys don't know what that is. I'm sure that's not true. Some of you know, but I'll tell you. It is something called the master symmetries of this equation. And by using these things, I have found that this result of Slepian, in a very specific case, certain Bessel integral kernel, can be extended beyond what Slepian did, and whereas Slepian found, Slepian, Landau, and Pollak, they all work together. Whereas they found one case, we will find a family of cases parameterized by continuous bunch of parameters where the same phenomenon works. The classical result of Slepian has already played a very important role, signal processing, that was the initial thing, but also in random matrix theory, and I'll show you one or two instances of that, okay? These I would like to enlarge, that's why. Okay, so here is a paper by Craig Tracy and Harold Whittam, where they are talking of the Bessel kernel. The Bessel kernel, okay, here already there are, oh, this is perfect. So the classical kernel, the sync one, will appear later. There is an example involving the 80 kernel, and then here, down here is the Bessel kernel. You can barely see that one. And this has relevance in the case of random matrix theory. There is another paper also by Tracy and Whittam, where they are involved with the 80 kernel. Okay, so here is the kernel that we are going to look at in a moment. And then for the 81, they found again that there is a commuting differential operator. Actually, my interaction with these friends of mine, they wrote me an email saying, you have been thinking about commuting things. Do you know how to find one for 80? So it took me about 2 days to sit down and do it. By the time that I answered, they had already found it themselves. Okay. Now, before I go on, I want to show you how this Korteweg-de Vries equation has appeared in places where you don't expect it to appear. Maybe I should spend 1 minute giving you my philosophy on this. I like to think of this nonlinear partial differential equation in some sense as an analog of the heat equation. This is physically totally stupid what I just said, but the heat equation appeared at one point. The tools that Fourier and others developed to handle it have invaded all of mathematics and have become extremely useful, way beyond the heat equation. I think something like that could be true in the case of KDV. So here is one paper. If you look at the title seems to have absolutely nothing to do with the KDV equation. However, if you look somewhere here, it says the moduli space of Riemann surfaces is governed by the KDV hierarchy of integrable equations. And that's exhibit number 1 for what I'm saying. Here is exhibit number 2. Witten came out with a conjecture that was eventually settled by Maxim Kontsevich. It involves the matrix value 80 function. And if you look here, here is KDV once again. Okay, so these are 2 examples showing that KDV is good as a tool beyond the initial thing. Closer to home, if you look at this beautiful monograph written quite a few years ago by our friend Bill Helton, he has, so this is the title of the little book. He uses the Siegel-Wilson, I don't want to explain what that is, machinery for KDV to do things that you would say have nothing to do with KDV. Well, that's, I rest my case. So now let's go back to the very, very beginning. I want to talk about what I call the Shannon problem. Okay, and here we're going to see specifically the case of this sine kernel. So you have a signal of an unknown signal. It has finite duration. That's what is called time limiting. The data that you know about the function are the values of the Fourier transform in this band, minus W to W. Okay. Of course, in practice, you only know this data in a very noisy way. Now, if you are a super pure mathematician, there is an immediate answer to this. What is the best use you can do? Well, you can say, I'm going to do analytic continuation. Let me not make any comment about that. That is not going to work. Let me just assure you of that. Okay. So the question is, what is the best use you can do of this information here? And well, here comes Gauss, if you want. So in general, let me pose the problem in this way. You have the data is known, but only over a certain set. So the B refers to the band limitation. You only know the Fourier transform of the unknown over a certain band, okay, that minus W to W, and you also have this a priori information that the function was supported in the interval minus t to t. I'm using A and B as the sets and the operators. So you do the thing that we teach in class all the time. The equation that you have, you write in this form. Instead of writing F, I write AF. So this defines the operator E that I was talking about before. So E consists of chopping in physical space, going to the Fourier side, chopping on the Fourier side. And to look at this, to analyze this, you have to form E star E, and you get these operators here, depending which order you do it. Okay, this is all very, very simple, but very important. And this is what these people, Slepian, Landau, and Pollak, did way back then. You write down explicitly, this is a very useful exercise to do, that the operator E star E is this finite convolution integral operator. And this I call the time and band limiting operator. Okay? You can prove in many ways that this fellow has simple spectrum. The spectrum is in the is discrete, is a compact operator. and is in the interval 0, 1, okay? And now here comes the important thing, that you can write down this explicit second order differential operator. You have to consider a certain domain for the operator, of course. That is, you have to consider certain boundary conditions, which in this case are trivial. Just being bounded is all that you need. This operator has simple spectrum and commutes with the integral one. So this is the phenomenon that I learned from that book by Harry Dim and Henry Keane when they were talking about the work of these guys. So this operator has now spectrum that is very spread out. So if you wanted to compute the eigenfunctions of the integral one, don't even try. Compute the eigenfunctions of this guy. They happen to be the same. That's the whole point. Why is this working? That's my question. Let me quickly do a numerical illustration. You can say, well, after all, who cares about this? I mean, maybe we can do that anyway. Well, I want to show you that even for a very simple 6 by 6 matrix case, you have a matrix that is very full, 6 by 6, that's pretty full. And this is the analog of your E star E. You can compute the eigenvectors of that guy very quickly, use the fanciest possible QR algorithm in LAPACK, and you will find the eigenvectors. And here are, as the columns, these are the eigenvectors of this 6 by 6 matrix. If I knew more tech, I would know how to make everything appear here, but I don't. Should you trust this? Well, what you can do is you can find a matrix, which I'm going to call op, which is tridiagonal. That's going to be the analog of our second order differential operator. And that matrix will have, in theory, the same eigenvectors of the initial one, and LAPACK QR returns these numbers here. And the question is, are they the same thing? They should be technically the same thing, but just look at this. Form the matrix of inner products. Now, if they were the same, up to order, you should get the identity matrix. And look at the matrix that you get. You have a 1 here, and then all these tiny numbers. So this is very good. In the next column, you already have some slight difference. In the next column, it's getting worse, 9, 9, 2, 3. This should be all just a 1 somewhere, and then everything else should be a 0. The other 3 columns show you that what you got is garbage. So the computation done with the best possible numerical algorithm of the eigenvectors of the 6 by 6 matrix, when the spectrum is very close together, can give you total garbage. Instead, you should use the other one. So this is just a small illustration. So this is just what I said before. Let me go back. The entries, this should just be the identity, and the eigenvalues of this is going to be appearing later in the talk. This is going to be, in our case here, is a tridiagonal matrix. In general, it will be a second order or maybe slightly higher order differential operator, but its eigenvalues are very separated, and the corresponding eigenvectors can be computed in a very stable way. Okay, so this is a summary. If you're lucky, you have something that is naturally appearing, this integral operator K. You can pray that there is a commuting second order or local operator. Well, your praise most of the time will not be answered. This is a very, very unusual thing. Why does it appear sometimes? That's what I've been trying to answer for a long time. Okay, so now I'm going to go back, forget about numerics, which are actually in this setup extremely important. Okay, I mean, if the commuting tridiagonal operator were to have spectrum that is very, very close together, then you haven't really done much. You can write some nice papers, but it's not going to help anyone. Okay, so I'm back to this question of the commutation between integral operators that appear naturally, I emphasize that, and differential operators. So here are some old and new results. So the old ones, again, my text is not what it should be. I don't know how to get rid of these spaces here. So if you go back to the papers, I'm going to concentrate on one of the last papers, which was written by Slepian. Look at this operator. Nu is a constant, okay? So this is a Bessel type operator, and you're all familiar with this one. It appears all the time because it is the radial part of the negative Laplacian in Rn, where the relation between the nu that appears here and the n is given by this formula here. So in particular, this includes the Fourier transform. If you take nu to be equal to 1/2, then you have this operator, okay, and its eigenfunctions will be the exponentials, and you're going to have the Fourier transform. In general, you will have this spherical or Bessel transform floating around. So for the initial operator, we know the eigenfunctions, and you can write them explicitly. These are the ones that are bounded at the origin in terms of Bessel functions. There is nothing really. I'm just relating to you the results that you find in Slepian and company. Of course, they didn't invent this either. This was known since the days of, who knows, certainly Bessel, maybe before that. As I said, the Fourier case can be obtained as a special case. And we know that in that case, this was the kernel for an integral operator. And I wrote before the commuting differential operator. Okay. Now, what Slepian did was he managed to extend the result that they had done to the case of an arbitrary nu, and I want to show you that. For an arbitrary nu, you consider these eigenfunctions in terms of the exponentials. You consider an integral operator whose kernel will be obtained by integrating over a certain interval. Well, in his case, it was space. For me, it's going to be time. The product of these eigenfunctions, and this is going to be acting on a finer interval. This is, so the t here has to do with, say, time limitation. The g, the fact that it's finite, has to do with band limitation. You can exchange the use of these words. What he found is that there is an operator not very different from the one that I had shown you a moment earlier. But yeah, here it was, the one that I had before. He found something very similar. You just have to add this little piece here. This piece here. Make a note of the notation A sub mu. This operator was found by Slepian. It commutes with the integral operator in the same way that the prolet spheroidal guy commuted with the sinc kernel, and it has this form, and it's going to appear quite often later in the talk. So just when I write A sub mu, I'll try to you try to remember that it's this guy over here. Okay, so those are the old results. What about the new results? What I will, the whole point of this, what I've been doing is consider this operator here. If you don't look at the last part, this is a particular case of Bessel, okay? Now notice that I'm adding here an extra part in the potential. There are some functions theta sub I. Here, my I will go 2, 3, 4, 5, and so on, in principle forever. I will put in here some functions theta sub I, which depend not only on x, but on parameters t. And I'm going to pull them out of some hat later on. When I write t, the t will have several components. I consider this operator, think of this as the analog of Bessel, but now it has this piece added here. It has some eigenfunctions. I don't want to make explicit the t dependent because it's just too difficult for me to do the tech. So everything here depends on these parameters that will appear later. You form some integral kernel for an operator acting on some finer interval. Notice, again, here we have time limiting, here we have band limiting, okay? But now there are these crazy guys that have appeared here. And what we try to do is we look for an operator that I'm always going to call op. I don't know how to write too many other letters in tech. And this operator will have these manifestly self-adjoint form with factors here that ensure that when I do my integration by parts, I don't have to restrict the domain. So this has a very, very large domain. And these coefficients here will be certain kind of Laurent polynomials. I mean, the details do not really matter, but the property will be that if you let the operator act on K in one variable, you get the same thing as if you let the operator act on the other variable. This doesn't guarantee commutation of the corresponding operators, but because the boundary terms are killed by themselves, this is all that you really need. So you look for an operator like that, and I found, the first example that I found is that this operator exists, and look at the beauty here. Let's stay at this for a moment. I call it the beauty. You may want to have some other name for this. The operator involves this A sub nu of Slepian. The operator that I find now depends on this three parameter T1. I haven't told you what that T1 is, but it involves A2 and A0 and some constant here depending on G and T. So it's a polynomial in the ones of Slepian, okay? And that's what happened when in the previous slide, the I has been set equal to 2. Now let's look at another few examples. For I equal to 3, I look for an operator. Now I cannot do this with order 4 as it was before. Now the order is going to be 6. So you do the same thing and you look, and lo and behold, you find that there is an operator that commutes that has this property here. Now it will depend on some parameter called T2, not T1. And again, it's a polynomial in the Slepian guys. A sub 3 appears here and A sub 1. Okay. I think I have 2 more examples to show. The next one is this one. I equal to 4. Now you need an operator of order 10. See, somebody could say, well, when you discretize this, your matrix will have quite a few non-zero diagonals. That's okay, but this is infinitely better than having an integral operator. And again, these operators happen to have a very, very spread out spectrum. You can write explicit formulas. I didn't want to show everything here. So this operator already depends, for instance, on T2 and T3. And you have to believe me that this keeps going. Don't worry too much. This is the last example. For I equal to 5, I end up getting an operator of order 14 by the time that you look carefully here. And this one depends on T3 and T4 and T3 and T4 only. Okay. So that's the end. So far we haven't seen the Korteweg-Lewis equation, and that's what I'm going to do now. So I'm going to assume, sorry for those that know this stuff very well, I'm going to assume that you have never heard of the Korteweg-Lewis equation. Okay, this is from around 1880, something like that, a long time ago. So here I'm writing down the Korteweg-Lewis equation. It came from water wave theory. Okay, and it's a nonlinear PDE. It has 2 terms that have physically very different meanings. Now, this subject bloomed in the 70s, 1970s, and it brought together huge number of pieces of mathematics together. Lots of things are known. The one thing that is important for us is what is written here. This is the second one in a hierarchy of equations, of which the first one is just translation. So this is a very silly linear equation, but this is the one that comes immediately after in a certain hierarchy that can be written down. Okay. The other flows in the hierarchy are obtained in the following way. You take x0, which is the infinitesimal generator of translations, this u sub x, and you apply powers of what is called a Neuenhuis tensor, and here is the tensor in question. So if you wanted to write down, if you want to get this right-hand side, all that you have to do is you have to apply this particular pseudo-differential operator, if you want to use that name, to u sub x, okay? Well, so those are, I have introduced for you the so-called KDB hierarchy. Well, this KDB hierarchy has all sort of properties. It is, for instance, Hamiltonian in an appropriate phase space of functions, okay? And here I should have mentioned many other names. For me, the important thing is that it's what is called bi-Hamiltonian, which really means it can be written as a Hamiltonian in two different forms. This notion was invented, as far as I'm concerned, by my Italian friend Franco Magri in Milano. And then other people also did this, and there are lots of other people. I mean, if I make a list of everyone that has worked in this area, we need to have a full 4-hour meeting. A very important consequence of being bi-Hamiltonian is that there is another hierarchy of flows, which is obtained in the same way as before. You apply powers of this Neuenhuis tensor, but not to the infinitesimal generator of translations, but the infinitesimal generator of dilations, which I have written here. So there is another hierarchy. Remember, in some part of the title or somewhere, I talked about the master symmetries of KDB. That's what I'm talking about now. So this other hierarchy has infinitesimal generators that are obtained by, you take translation and you take powers of this Neuenhuis guy. And here I'm writing down the first few. It is not totally trivial to compute these things. If somebody knows how to do the 17th one, let me know, okay? So I wrote here a few. There are some evolution equations where on the right-hand side, you're going to put this. In that case, you simply have dilation. Or you're going to put that one, in which case you're going to have the first master symmetry of KDB. Here is the second master symmetries. There are these antiderivatives. You have to interpret what you do at infinity carefully and so on. But I'm just trying to give you the flavor of this. One can show that the KDB flows, the ones that you obtain by applying, starting with the translation and then powers, they commute with each other. The other ones do not commute with each other. They have some very interesting commutation relations with the x sub j's themselves and then among themselves. Okay, and these are called the master or additional symmetries of KDB. So out of the hat, I took these things, and you may be wondering why on earth is he wasting our time with this? So I want to answer that question now. So what I have found, by the way, is that more than the KDB hierarchy itself, it is the master symmetries of KDB that plays a role in our problem. So I'm going to show you that now. So I said I have managed to extend the result of Slepian, which started in this way, by doing some deformations. I take these operators and I add to them these potentials. So the part that I'm actually adding is this part here. And the question is, who on earth are these V sub i's? What do they have to do with the master symmetries of KDB? And I'll just write some few formulas. So if you let V2 evolve in the variable T1, that's exactly the same thing as applying tau 0 to V2. So it may be more natural to write what I write here as the right-hand side, exchange right and left. So there are some nonlinear evolution equations satisfied by these V's, which feature as the infinitesimal generator exactly these members of the hierarchy of master symmetries of KDB. Okay. And well, there are some fixed points, just if you want to come in. Don't worry about any of these. This is totally irrelevant. Now I have to tell you, as I'm coming hopefully close to the end, where do I get these theta sub i's? I never told you where the theta i's came from, okay? And now I'm going to tell you. Back, actually, Bill Helton was mentioning yesterday that IOTA started in 81. Well, in 81, I was very lucky. Hans Doistermatt, my dear Dutch friend, was here. We got together in this project, and 5 years later, we wrote a paper, but it started in 81, where we found some connections that I'm exploiting now. So these functions that I write here, theta 0, theta 1, theta 2, and so on, if you look here, they are functions of x, but they depend on some parameters. Here you have t3, t2, here is t3, t4, t5, and so on. Those functions, this is just copied from that paper with Hans way back, okay, 40 years ago in terms of when we found these things. And these functions we found were 1/2 of the solutions of what is, we didn't call it like this. Some people have started calling this the bispectral problem. That is, the question is, you consider this Schrödinger type operator that has eigenfunctions depending on the eigenvalue parameter z. I'm sorry, this is a typo here. The lambda should be the same as z. To fix this someday. But they also satisfy this so-called bispectral property, that there is a differential operator in the spectral parameter that has the same eigenfunctions as eigenfunctions with an eigenvalue now that depends on x. So that was the problem that we formulated. My motivation back then was really this Slepian Landau Pollak problem, and I thought, well, this may be of some use. So we solved the bispectral problem back in there. We discovered all sort of unexpected connections. So let me just briefly mention some of them. Connections between what and what? Between the bispectral problem that by itself doesn't have anything to do with anything. This is just a problem all by itself. We found that it is connected with integrable systems, a la KDB, TODA, etc. There are some very special monodromy properties for the eigenfunctions. There is something called the Darboux process, which I don't have time to talk about. And we found that in our case, there were two families of solutions. Some of them really have to do with the master, with KDB itself. If you look at the tau functions, which are the thetas that I had indicated before, they are exactly characters of certain irreducible representations of GLN, and they give rise to the rational solutions of KDB. Then we found some other family of thetas, which are exactly the ones that I displayed a moment ago, these thetas. We wrote them in there. Hans didn't want to have so many of them shown. I said, listen, 40 years from now, when I look at this, this is going to be what I care about. Anyway, so the other ones, we found them. I'm still looking for some group theoretical interpretation of these guys. This should be the character of some group, maybe. If you know, give me a call. Call me collect at 3 in the morning. I won't get mad. What Magri and Giubelli, who was a student of mine, found later on is that they are actually the rational solutions of the so-called master symmetries. So if you look at our paper with Doistermatt, we never identified the role of the master symmetries. This was done by Magri and Giubelli later on. And then there are some so-called add conditions, which is a certain nilpotency condition in terms of Lie algebras that we found. All the things are completely connected with each other. Okay. Well, what we didn't do back then is to show that all of these eventually serves at least half of it. The part that has to do with the master symmetries gives you a way of extending these commuting properties in time and band limiting from the cases of Slepian, Landau, and project and Pollak. As I say here, this was the initial motivation for the paper with Hans, but we never got that far. In fact, if you read, I say that in there, but this is something that got Hans pretty unhappy with me. He said, you should never talk about what you're trying to do 20 years from now. You should talk about what you have actually done. Well, this was his way, but I managed to stick a sentence in the paper anyway. Okay, so now I'm very close to the end. So we have now a huge new family of commuting pairs of integral and differential operators, depending now on tons of free parameters. And you can say, well, this is very nice math and so on, but I'm interested also in applications. I mean, I have the feeling that these two things actually work together all the time. So I just want to go back to a very old paper. We wrote a paper with Long and Prostad, where we did everything, but not on the real line or on Rn, but on the surface of the sphere. So we did the appropriate harmonic analysis involving functions defined on the sphere. But in that case, I sort of stopped from thinking of any applications. Well, many years later, there were people in geophysics that found that what we had done was exactly what was needed if you want to consider the similar problem, similar to the one of Shannon, but in the case of the sphere. And there are, you can imagine, similar things for hyperbolic space and other cases. So if you read, these are the papers I'm talking about, and they call these things very properly the spherical Bessel Slepian functions. This is one paper. So there are applications in other areas. For me, the big question is, what about these new ones, the ones that have to do with the master symmetries of KDV? Will they be useful for something? I have no idea. So these are a couple of Hungarian guys that found the paper that we have written with Longi and Prostad useful. And I think you are lucky. And this is my very last transparency. And this is it. So I managed to do what I wanted. I managed to finish 11 minutes or 12 before the hour. Thank you very much.
Now we can clap.
Any questions for this?
Well, but there's also a question from first. This is the question online, shall we? Yeah.
Professor Trigiani, please
Yeah.
go.
Yeah, may I ask you a question, please?
Sure.
You have, for instance, a compact operator defined on, say, -1, 1, and then you have a differential operator, presumably with boundary condition. So what is the notion of commutativity? Usually for unbounded operator, commutativity means that the resolvent commute because of the issue with the domains.
Now, let me answer with a practical answer. They share, both of them have discrete spectrum, one can prove that,
Yeah.
and they have exactly the same eigenfunctions. I should say they have simple spectrum. Did I say that? I hope I said that.
Yeah, you said that, yeah.
Yeah. So this is the best possible world. And in practical terms, if I go back, there were some, I don't know if I'm going to find this, but at some point I wrote, so there are many ways. Yeah, here is the condition. So this is the kernel of the integral operator, and it depends on two variables, of course. And acting with the differential operator on one variable is the same as acting with the other one. Okay, this is the existence of such a differential operator is far from trivial. In fact, it is very exceptional. And this, plus the fact that I have a very large domain, is what I want. I'm not sure this answers your question, but that's
yeah.
my
So
answer.
it's a certain way of defining the commutativity.
Yes, yes, yes.
Okay, I understand. Thank you.
I had a quick question. There were these Virasoro constraints, basically. Virasoro symmetries of these KP and KDV hierarchies. They were described in, Pierre van Merbeke's papers as well, somewhere late 70s, beginning 80s, and there was some geometry in there too, as far as I remember, some Grossmanian action and so forth. So you were thinking of the geometries of these. I believe that those can be found also in some of those van Merbeke papers a while ago.
Well, we need to talk more. Let me see if I find that. Let me just go back. I said, where am I going to find something here? My question, when I say geometry, if you want, here is my question. Take these potentials, okay? Consider the appropriate Laplacian with this potential added. Is there any symmetric space somewhere or something for which this is the radial part of the Laplacian? And although it is true, I mean, since you mentioned Pierre is a very good friend of mine. I need to, here we go. If you look, there is a paper of Pierre no, this is Pierre all by himself, where he actually writes down this second, I mean, the first non-trivial one. So let me be very upfront and say, I hope that what you say is true, but we have to talk more about this. As far as I know, these potentials, which are solutions of the master symmetries, or for that matter, the ones that go with KDV itself, have not been connected with any geometrical object. I could be wrong, but if I'm wrong, I will be very happy to be told that. Okay. Yeah, there are some short notes by Pierre. I forget what they are called. String equation, some other things, and there. It is, to my mind, the best, the most accessible presentation to the master symmetries, but I still don't think that there is a geometrical object behind. But if I'm wrong, please tell me. Okay. Thank you.
I'll try to look it up and send.
Yeah, that would be. Yeah, thank you. That would be fantastic. That would justify this talk for myself. Yeah.
Any other questions? Well, let's thank the speaker again.
Right.